And we are on there. Hi, Prasmit.
Hello.
Hello. Is this the correct pronunciation, Prasmit?
Yeah, surely.
Oh, fair enough. Welcome and thank you for joining us. Where are you speaking from?
Yeah. I am from New Delhi.
Oh, nice.
Fantastic.
And tell us more. Okay, let's just start introducing ourselves.
Okay.
Okay, I would like to Vinicius first. Could you please introduce yourself?
Okay.
Okay.
Well, hi guys. I'm Vinícius. I'm Brazilian. I'm 20 years old, and I'm studying physics since 2015 in the Federal University of São Carlos, and I'm here to talk to you about the history of quantum theory, the beginning of quantum theory in the beginning of 20th century.
That's nice. Prasmit, would you please introduce yourself?
Okay, I am Prasmit and I am a first year student of BTech. I am pursuing BTech from Electronics and Telecommunication.
Nice. And you speak from New Delhi, India, right?
Yeah.
Fair enough. Um, I'm Augusto. I'm an engineer. I'm currently pursuing my master's in acoustics, and I'm working with materials for aircrafts and spacecrafts to try to, let's say, distinguish the noise in some frequencies within the main cabin
Oh,
of the aircrafts. So that's basically my research. And welcome to the first episode of AstroTalks. And the idea of these meetings are just to discuss about physics and make new friends and try to ask and answer and discuss some natural questions on some topics of astronomy and astrophysics. Uh, okay, so I'm going to start asking a question to Vinicius. Vinicius, what's your research mainly? What are you doing right now? You told us that you work with some ceramics and work with some condensed matter physics, but what's the objective of your research right now?
Well, I'm working with uh, magnetoelectric thin film ceramics.
Mm-hmm.
It's the idea of the project is joining two different ceramics, one with piezoelectric property. Piezoelectric property is a property of a special ceramics that can transform electric field into pressure and pressure into electric field, and magneto strictive ceramic that can transform pressure in magnetic field and magnetic field in pressure. And then the idea is joining them into a film and a nanometric film, and they will be bounded by the pressure property. And then when I apply electric field, I have magnetic field, and when I apply magnetic field, I have electric field, and I could use it to make computer memories that are, I don't know, 2 times more efficient than the regular ones.
Fair enough. And this efficiency, it is only in terms of storage or also in terms of processing information?
It's a good question. I guess I haven't analyzed it yet because we're just studying the properties of the materials and characterizing it.
Mm-hmm.
This is a efficiency is a engineering work.
Mm-hmm.
My job is just have the theory bounds of this, you know?
Oh, fair enough. Okay, thank you. Presmit, do you have any questions?
yeah, I was asking whether it's based on Faraday's induction law. I
Sorry,
mean, the first. I was asking whether it's based on Faraday's induction law.
Okay, the induction law. Um,
Um, I mean, how he created the generators. Like FDI principle, force is applied that causes a magnetic force and which causes something motor to rotate.
Okay, and the motor to rotate, is that what you're asking?
Yeah, I mean, is the principle similar?
Ah, okay. Did you get the question, Vinicius?
No, sorry.
Okay, he's asking if the principle of, because you know that the electric motor, it has an electric current that goes through its magnets, and then this electric current, it creates a magnetic field which makes the rotor to rotate. And Prasmit is asking if the ceramic you are researching right now has the same principle of it.
Oh, I guess no, because this principle is kind of Ampere law and Lenz's law.
Okay.
It's a
Lens law.
electrodynamic law that associates electric current with magnetic field. What I'm doing is associating, is making how can I say, a cheap material that could work in high temperatures, just like I don't know, the board of the personal computer that could
Okay.
work efficiently with high values of electric fields and magnetic fields.
That's really nice. I am just answering John Rick because he is asking some questions on Facebook. So I asked him to ask the questions here on the web chat. And now we have Jose. Is it the pronunciation correct? Jose, are you listening to us? And he's offline. Okay, fair enough. Hi, John Rick. We are looking in the chat, and we are reading everything you write. So do not worry. You can always communicate from here. Is that fine for you? I guess so. So no worries, John Rick. It's a pleasure having you here. And so, Prasmit, are you carrying any research right now?
No, I entered the university. It has been 1 year, and it's a trend to begin from the second year.
Oh, fair enough. And how does university works there in India? Like how many years you have before you pursue a degree?
Well, of course, 4 years for BTechs, and for BSc and other courses, it's 3 years.
Fair enough. And that's nice. Have you guys got any questions regarding any of your researchers so far?
No,
Okay, fair enough.
I mean, we are learning basic mathematics and physics, advanced version of what we learned in our senior years.
Okay, that's nice. And why did you choose to pursue this degree?
Well, because it is fun, and even there I like to solve problems in physics, so I thought this is the best way to enhance my aptitude for solving questions, and that's why I think I want to pursue physics as my career. And though I am not very good at astrophysics, but I have read basic astronomy
Oh, fair
and
enough.
all facts. I mean, not good in reasoning, but I know the facts of astronomies a
Mhm.
bit.
That's nice. That's nice. So I'm going to give a word to Vinicius, and the main topic of this first hangout is quantum physics and the history of quantum. And this is a subject that attracts many people to physics. And generally, when you are having a discussion with or an argument with someone, you just say, "Oh, according to quantum physics, something that," and then you basically win the argument, because if you put quantum physics in the middle of the argument, it means that, oh, we have a badass over here. That's nice, John Drake. John Drake is saying that he loves astrophysics. And John Drake, I'm gonna ask you a question. In what year are you? Are you already in the college? Are you still in high school? And while John Drake is answering to us, let's go back to quantum physics. So,
Okay.
Vinicius, what was the starting point of quantum physics? Um, And that's nice. John Drick just said that he's in high school. That's really nice, John Drick. Oh, fair enough. Wikipedia is a really important source of information because it is open source right now. Fair enough. So going back to quantum physics, Vinicius, what was the starting point of quantum physics in the history of physics, and why was it that important?
Well, I guess I'll start telling about the book I'm using to find information. This is Iceberg and Hesnick. If you study physics, you know these authors. I don't know, maybe Resnick, but Iceberg is famous too. And I guess it's a great book, even to people that doesn't have a lot of mathematical uh,
Background?
skills, because it tells a lot of stories,
Yes.
and there's a lot of qualitative analysis. So I guess it's a great one for you guys to find. You can find in, I don't know, every college must have this. I no idea. But well, we have to think about what was happening in Europe on the transition of the 19th century to the 20th century. There, we were watching Industrial Revolution and the second one, I guess. And there was electricity, and they are, I don't know, starting to comprehend that it was not uh, a fluid. People used to think that electricity was a fluid, just like air, just like water, and I don't know, they used to think that the electricity of the neuron, your brain, was different electricity from the lightning, and people were joining this in one single theory with Maxwell, with Faraday, and then there is a conference in 1904. There is a conference,
Hmm.
and Lord Kelvin. Have you ever heard about Kelvin, the Kelvin scale
Hmm.
of temperature? Yeah, it was a guy named Kelvin. Lord Kelvin says that there are only two problems left to be solved in physics: the problem of the black body and the problem of the precession of the orbit of Mercury.
And what's a black body, just for the audience to understand?
Yeah, a black body is basically an ideal body that can emit and absorb uh, every single frequency of light of electromagnetic spectrum.
So it
And
does not reflect light.
yeah,
It's basically
that's
like
the
a black
name.
hole.
It's called black body because it absorbs every light that touches it. But great bodies that can absorb light really in a good way can also emit light in a good way.
Hmm.
So uh, there is an ideal body that has this property. So what's the problem with the black body? They could measure the the electromagnetic spectrum emitted by intensity, but they could not comprehend the mathematical idea behind it. The model was not really right. I have an image here of the graphic. I don't know if you can see it. It's clear?
Yes, I can see the curves, but I cannot see the titles of the axes.
Okay, this is the frequency
Wind
of
slow.
electromagnetic spectrum, and the y-axis is the intensity of the
Hmm.
light in each. So, and the lines, we have three lines of graphic here, and they are
Hmm.
respective to different temperatures. The small one is to a low temperature, and the large one is to a high temperature.
Hmm.
Okay.
Vinicius, could you please show the graph again because John Drake is not seeing. John Drake, are you seeing the graph right now? In the x-axis, we've got frequency, and in the y-axis, we've got intensity. And what the graph is saying is basically that the intensity of light varies with frequency.
Yeah.
Okay.
So basically, what we have here is a body. I don't know. Think about coat. When you're doing a barbecue
Mm-hmm.
and you look inside the blaze and you see that the coat is orange.
Mm-hmm.
It happens because at that temperature, the most intense frequency that are emitted by the coat is the orange light. You guys understood it?
Mm-hmm. I did.
Okay.
Razmit, did you understand?
Well, I actually the sound is a bit low, so I lost somewhere.
Oh, sorry.
Okay,
Well,
I'm going to mute my microphone, okay, so that you are not disturbed by my noise. So, Vinicius, could you please just give the same explanation again?
okay. Think about when you're doing a barbecue
Okay.
and you look to the coat and it's
Good.
burning and you see that the coat is orange. It's shining a orange light.
Yeah. Yeah.
It happens because at that temperature, the most intense frequency of light emitted by the coat is the orange light. And they could observe that every body, every matter that has a temperature is emitting light, is emitting electromagnetic light. So when you think about I don't know, uh, uh, well, you have a temperature and you're emitting, I don't know, infrared light. So we can, I don't know, have you seen spy movies and they use that glasses that can see
Yeah.
infrared spectrum and they see people through the walls? It's because you're emitting infrared light at your temperature. So what happens is that they could not explain how it could work mathematically. And then there are some experiments like Stefan Boltzmann see that the intensity is proportional to the
To the power
temperature.
4.
What?
Temperature to the power 4.
Yes, right. Great. And then there's
Okay.
Vane, and he sees that the product of the temperature with the length of
Wavelength.
wavelength is proportional to a constant. Yeah, it's great. And then Raylight engines try to explain this. Raylight engines were two physics from that time, and they're trying to model a whole theory explaining how could it work. And it was not a phenomenological theory. They were not starting from the experiment. They were starting from physical laws of the classical physics to understand that properties. And they found a equation for the radiation of a black body, but it was kind of wrong because when you get close to the ultraviolet frequency, it
Yeah.
diverges to the infinitum, and we have this problem here.
Yeah.
You guys see? So
Yes.
this is the experimental,
Mm-hmm.
and this is the theoretical graphic.
So it's really, there is a real discrepancy between the theory and the experimental results.
Yes, and then they got surprised because there was no mistake in their assumptions. They were using physical laws that were right to every other problem, and they could not understand why it was not right here. And then came Planck. Have you ever heard about Planck? And
Sorry, you are not.
what?
Well, you were not audible for a few seconds there.
Okay, sorry. But I have heard about Planck. Could you just go on?
And then Planck have a glimpse of the mistake. It was not actually a mistake, but he thinks, what if energy is not continuous? What if energy actually is discrete and divided in little packages? And he makes a correction on their assumptions, thinking of the energy as a discrete physical property.
That's nice. Vinicius, sorry to interrupt, we've got a question from John Drake. And he asks, is the graph only applicable to black body radiation or to all types of electromagnetic radiation?
Well, it's referring to the emission of electromagnetic radiation from a black body. But you can adjust it to treat everybody with this mathematical model, adjusting a constant called emittivity. But it works. I will talk about how we can use it in astrophysics later, and you shall see that it works in an approximation, in a qualitative analysis.
Nice, thank you.
So, and then Planck thinks about quantizing energy. What is quantizing? It's quantizing, I guess. I don't know if this is the word, but
I guess the word is quantizing.
Quantizing, thanks. Yeah, it's different from quantizing, I guess.
Yes.
Yes, and it quantizes energy, and we have this drawing here. If you think about now, it's not continuous. We have some steps of energy adjusting with the graph. If you think about it, it's nearly what Newton used to create the calculus. If you think
Yes,
about
because
that.
you have the curve,
Minimize.
and he is splitting the curve in little rectangles, right? So
Yes,
if
yes,
you
right.
split it in infinite rectangles, you've got what we call an integral,
Yes,
which is basically the area below a curve.
yeah,
So I
but
have one question.
yes.
What is the condition for quantizing? I mean, what is the required temperatures where the quantization takes place and others are eliminated?
I don't understand. Could you repeat?
I mean, they have been quantized. So what is the condition for quantizing?
What is
What
the
are
condition?
the condition? Yes, for the quantization.
Okay, actually, the postulate says, I'll just read it here. Here, any physical entity with 1 degree of freedom. 1 degree of freedom is that it can move in just one direction, whose coordinate is a sinusoidal function of time. So it's oscillating in
Okay.
time. Think about a particle oscillating.
SHM.
That's nice. It's basically the same as we have an air particle
Wave.
oscillating in a sound wave.
Yes.
Perfect. John Drick has a question as well. What do you mean by quantized?
Oh, yes. When you say that a physical entity, a physical quantity is quantized, you're saying that he's a multiple of constants that we call quantum. And this multiple is always an integer number. So if you think about, I don't know, dollars, think about dollars. Every dollar is multiple of $1, is an integer multiple of $1. Then you have the same. It's okay, but don't count it. Think about the $1 and every other value above this is a integer multiple of $1.
So if an object is quantized, I am basically saying that it's made of small parts of itself. It's something like that.
Yeah, when an object is quantized, you're saying that you can comprehend this as little packages of something of a minimum size. Okay, so yeah, I guess it's the right way to think when you think that is a minimum and you just can add and sum this. And I don't know, you catch 10 of this little coin, you have the energy, but
Yeah.
you can go and break this coin into
Mhm.
two pieces, okay?
That's perfect. I've got another question for you.
Yes.
John Drake, not for you, but I mean, I'm putting the questions on the table. If you know
Okay.
how to answer the question, just answer, press me or whatever. Um, John Drake Valdez from Philippines is asking, what are fuzzballs?
What are what?
Fuzzballs.
Fuzzballs?
Yes. Do you know how to
No
answer?
idea.
Okay, so let me answer. Um, um, Fuzzballs is a concept from the string theory, because when we talk about the theory of black holes in the modern physics, what we have in the center of the black holes is a singularity. Okay, so it is a point where all the laws of physics break. Basically, the idea and the concept of fuzzballs, it comes to overlaps two difficulties that we have in the modern physics. And the first one is the paradox of information. Because according to modern physics, what we have is that after the the horizon events of a black hole, uh, you cannot see anything. So the theory says that the information is lost. And what fuzzballs do and is that this concept replaces the singularity within the black hole, and says that everything that is inside the event horizon of the black hole are strings, the small strings from the string theory. So just a brief concept. String theory says basically that all the matter and everything that we know is made of little strings that are vibrating in different frequencies. So basically fuzzballs, they are replacing the singularity of the modern physics in the black hole, that we don't know how it acts, for small strings that in theory we can know how they work. So that's basically it. Fair enough, John Drick. Thank you. Sorry, Vinicius, keep going.
Don't care. So we have this quantizing of energy to the black body radiation. And it worked really well. Planck found a equation that could fit perfectly the experimental results. I don't know if you could see it, but here we have some dots, and they are perfectly fitted to the experimental line.
Yes, I can see. Yes.
So I don't know, it was a great victory, but Planck went really bad in doing this because he say that it was it was the spear. Is right the spear?
Like he was desperate.
Yes, yes. He was desperate to find the answer, and it was an act of desperation. But it actually worked. And then Einstein with the photoelectric effect, observe the same property of the energy of the light being proportional to their frequency multiplied by a universal constant, the Planck's constant. And it's really strong, it's really mind-breaking if you're thinking of, I don't know, 10 centuries of continuous properties of physics. Uh, but it actually solves many problems. And then the problems start to be solved, and the X-rays were comprehended, and it was a huge advance in the physics.
Okay, I've got a question. We have seen many advancements in the last months since the LHC was re-turned on,
Okay.
because we know that they were running some experiments to discover the Higgs boson, which was in 2013 more or less, and they shut down the experiment to make improvements, and now they are running it again. And this week we had some news saying that they had just kind of pointed and spotted different particles that were not supposed to appear. And basically my question is, how is quantum physics related to the standard model of physics? Are they the same thing? If I'm talking about quantum physics, am I talking also about the standard model, or are they different things? If you could comment on this.
Oh, okay. Uh, Actually, I don't know if I can answer it, but I guess yes. When you talk about quantum physics, you're talking about the standard model. But this, what we're talking here, we used to call this old quantum theory, because when Schrödinger and Heisenberg appears, they they make a change in the quantum theory, and this is the new and the modern quantum theory, the theory of Schrödinger.
Okay, so if we talk about Heisenberg and Schrödinger, we are talking about this modern quantum physics, and when
Yeah.
we talk about Planck, it's like old quantum physics.
Yes. Yes.
But we still use some Planck's thoughts, right? Some of Planck's theory is still available for the use today in this so-called modern quantum physics. Am I
Yeah.
right?
Yeah. Yeah. I guess the major problem with old quantum theory, it was the Bohr model of the atom that used and mixed concepts of classical mechanics with the concept of energy of Planck, and somehow it was not really stable, thinking of an atom just like Bohr did, and then Schrödinger and Heisenberg come to make it stable, and they do some assumptions that I don't know if I can talk here yet, but they try to change things, and uh, kind of using some new concepts and lefting old concepts behind. I guess it's the point. Well, so I talked about. May I keep on? I don't know.
Yes.
You guys can.
Do you have you got any
Yeah,
questions?
sure.
Yeah,
No,
say.
Okay, I think we have
I
10 minutes left, so 10 to 15 minutes. So take your time.
Okay, so I guess I talked about uh, Stefan Boltzmann law and Vien law, and so I guess it's time to say how can we use it to astrophysics. There are a lot of problems in this book, uh, uh, asking, I don't know, like we have this graphic of the emitting light of the sun, what the temperature of the sun. And we can do these exercises using these laws. We can do, if you think that the product of temperature and the maximum wavelength is a constant, and you have the maximum wavelength of the sun that is near the
Yeah.
yellow or green light, you can find the temperature of the sun. And you can use it to comprehend temperature of new stars and new planets that we find. If you consider the relativistic Doppler effect and find the correct wavelength that we're receiving from space, you can comprehend the temperature of galaxies and stars that are really, really, really far away from us using this old theory here. So I guess this is really powerful, yet it's not so applicable. We can understand space using this this
Model.
stuff that they gave us.
Okay, and John Rick is asking if this is the redshift, the so-called redshift.
Okay, yes, there's the redshift because of the relativistic Doppler effect. I don't know. Do you want to talk about Doppler effect? Augusto, you mess with sound.
Okay, so the Doppler effect basically says that the frequency of a sound wave or of a wave, let's say, that you are going to presentiate or receive, it will vary according to your velocity related to the source. So if you have a sound source here and you are here, the sound source, if the sound source is still, if it's static, basically what's going to happen is that the front waves will be traveling in your direction like this. Okay, so you have a front wave here, a wave front here, a wave front here. But if you're traveling in the direction of the sound source, the thing is that you are going to experience the wave fronts in a higher speed, right? Because let's say that if you are static here, you will have the sound source here, and the waves are traveling like this. But when the waves are traveling like this and you're traveling like this, you are experiencing more per second. So this is basically the Doppler effect. And the best example of it is the ambulance. When you hear an ambulance that is getting close to you, the sound tends to get higher in frequency, like and when the ambulance is going far from you, you are going to experience
Decreases.
the sound more lower, a lower sound, a lower frequency, like woo, woo, woo. And this is basically the Doppler effect. The closer you are getting to a sound source, the higher the frequency that you will listening, and the same, and the farther you are going to a sound source, and the lower the frequency you will experience.
Yeah. And then the relativistic theory, the special relativity says that the Doppler effect is valid to light too. So when you talk about the redshift, it's because the frequency that stars are emitting and we are receiving are actually lower than the frequency that they're emitting. So they are going far away from us, and this makes us think about the expansion of the universe. All the things are getting, I don't know, the distance between us and the stars are getting bigger. Uh,
Further.
okay.
Fair enough. Have you guys got any more questions? Vinícius, could you please continue? Do you still have something to say?
Okay. So I'll just mention one more thing
Mm-hmm.
that is about the. Have you ever heard about that temperature of the universe near to 2.7 Kelvin?
Mm-hmm. Yes,
So
I was reading some stuff like that.
yeah, we can comprehend it uh, when you see that Earth is receiving a really low intensity of energy from every side we look. And then you think, why we're receiving this energy? It's not from the sun, because the sun incites energy from just one side of the Earth. And then you can comprehend, and then making the calculus, it's equivalent to the energy emitted by a black body in that temperature or of 2.7 Kelvin. And it's since it's coming from every side of this globe, right?
Hmm.
Every way you look, you're receiving this. You
Is
say
it
that,
related to the noise that we hear when we turn on TV, which is without an antenna or something like that? That shh.
I don't know. I actually don't know.
Okay, fair enough.
One question.
Mm-hmm.
Yes?
I was asking that according to the new quantum laws, like Einstein's that photoelectric effect, it has been said that the energy doesn't depend on the wavelength, doesn't depend on the intensity. It rather depends on the wavelength.
Yes.
So how is intensity related to this? Like you have said now that they check the intensity of the light and do the required processes.
Oh, okay. You're asking what the intensity makes with my photoelectric system.
Yeah.
That okay. The intense is the amount of energy you're giving to your system. Think of the light as photons. Einstein did this. Think of your light inside the your plate as packages of energy. If you raises the intensity of the light, you're raising the amount of packages of energy you're inside in this, but not actually. And but the electrons in this plate, they need always that value of energy. I don't know. If you think
Cut
about
off.
hydrogen, you're thinking about 13.6 electron volts of energy to come and spit out the electron. So if you have a lot of packages, you're not, I don't know, giving more speed to your electrons because you're already,
Collision.
what?
Collision occurs.
Collision, yes.
Yes, you're just spitting out more electrons. So what you're doing when you raise the intensity is raising the number of electrons that you're spitting out of your plate, but not actually increasing their speed or any stuff of that. I don't know if I was clear.
Yes, for me it was
Yeah.
clear. Fair enough. Really nice explanation, by the way.
So I guess that's it. And then Borg come to try to explain the atom, and we have so many changes. I don't know. It's just the the first spark of the big changes we will see in the 20th century.
Fair enough. And I have one last question
Yes.
for you, Vinicius. What do you expect to see regarding quantum physics in the next few years? Like, what is the the biggest achievement that you're expecting to see in the next few years?
Wow. Well, I don't know if I understand really well what they're doing, but I expect more answers. It will be good about the beginning of the universe. And I don't know, maybe the black matter, uh, dark matter. But being realistic, I guess it will take us a few decades to comprehend just one more step because universe is really uh,
Weird.
complicated to understand.
Okay, fair enough. So thank you all. Presmith, have you got anything else to say?
No.
John Drick, have you got anything else to say? Perfect. So guys, thank you all. This was AstroTalks episode 1, History of Quantum. And next month, we are going to be in the episode 2, which is basically, the title is How to Become a Physicist, or How to Become an Astronomer. And hope to see you all there, okay? Stay tuned, and thank you.
Bye, guys.